Alright, so welcome to week 3. Let's see. So labs are graded. We already talked about labs. Hopefully you're making good progress on lab 2. I graded your homeworks and gave you feedback on that, and the homeworks looked good. Let me see what I actually graded on the homework. Oh, there we go. Alright, so for the homework I graded questions 1, all 5 parts of question 2, question 6, 11, 12, and 15. So that was 10 questions, 2 points each. And I thought those were representative of, basic assembly language programming using literals or using file registers. And I tried to give you a good amount of feedback if there was something going wrong with your code. But look over my comments, and if you're not sure what's going on, please ask questions or ask for help. The main things I think to keep in mind are the following. If you say something like move file register 80, right, that's working with the contents of a file register whose address is 80. It's register 80 in the memory. It has nothing to do with the number 80 other than that's the address, right? And this is a no-op. This moves from location 80 to location 80. If you do this, it moves from location 80 to the W register. If you want to add something and you say something like add WF1, right? This is a file register. It's not the number 1. It could have the value 1 if file register 1 happened to have the value 1 inside, but in general, this is a file register, this is a file register. Any numbers that you put after this operand, after this opcode, any of your operands, those are basically always file registers, unless you're doing a literal instruction or a bit instruction or a branch instruction. So if you see something like add literal to W1, that's the number 1. Okay, it's 7 zeros followed by a 1. But anything that these byte-oriented instructions, this is a file register. Okay, you can't specify a literal value. If you want to specify a destination of the W register, you can say comma 0 at the end. Okay, but 0 is not the W register. The W register is actually off somewhere else in memory. 0 is just a modifier we put on this operand that specifies a destination. All right. Any questions on the second homework so far? That's due on Thursday. And I, as usual, I'm logged in twice, so the place I'm logged in on my computer, I marked my name no questions, meaning if you send me a chat message there, I won't see it. Okay, but I'm also logged in on my phone, and that says questions, so if you send me a message there, I will see it, such as I just got. So can we talk about number 20? Not sure what that one means. Let me pull up the homework. Alright, so this is a series of questions related to doing input and output. Question 18 says you want to read from these 2 pins, RA2 and RA3. And let's pin down some terminology. RA2 and RA3. These are parts of port A. And instead of RA3, we might refer to port A angle bracket 3. It means bit number 3. And RA2 we could refer to as port A angle bracket 2. And if we wanted to refer to both of these bits together, we might say port A angle bracket 3:2. This is a 2-bit number. where the most significant bit is RA3 and the least significant bit is RA2. And be really careful whenever we talk about this stuff. The least significant bit is bit 0. The most significant bit is bit 7. Okay, these are just things you have to make peace with. Okay, so RA2, we call it bit number 2, but it's actually the third bit from the right. And RA3 is the fourth bit from the right, right? First, second, third, fourth. Okay, that can trip you up, so be careful around that. Alright, so in this question, you're asked to set things up so that you can read from those two pins and write to pin RA7. So you're going to write to this, and you're going to read from those two. And it's asking you what needs to be set up. Okay, so ADCON, TRISA, PORTA, all of that stuff. This is the initialization that you're going to do again and again and again anytime you're doing input or output on the PIC processor. Okay, so what do? You put 7F into ADCON 1. And then we set up the TRISA register. So 7F into ADCON 1. And then TRISA, each bit in TRISA tells us whether the corresponding bit in port A is an input or an output. And remember, 1 is input and 0 is output. Okay, we're told that we want to read from pins 2 and 3. Those two pins of TRISA have to be 1s. We're told we want to write our output to pin 7 of port A, so bit 7 of TRISA has to be a 0. And we do this up front. We do it before we actually do anything with port A other than maybe clear it. Right? So before we can read from port A to see these two values, or write to port A to set that value, we have to set up TRISA. Okay, and TRISA is telling us, are we writing or reading? So input pins, write a 1, output pins, write a 0. What do we put in the other pins? In some sense it doesn't matter, but they default to 1s. 1s are safer, so I would probably go ahead and say just go ahead and put 1s in these other positions also. Okay, but really these are the ones that we care about. So I would set TRISA to, in this case, 7F, same as we did ADCON 1. Okay, and then write code to read from port A and save its contents in register 78. Well, that could be a move FF from port A to hex 78, or you could move F port A, comma 0, and then move WF to hex 78. Those are probably your two main choices. And then question 20 is saying, tell me about the contents of file register 78. So 78 is going to contain 8 bits. What is the meaning of each of those bits? And this is a think about it kind of question, right? I'm going to copy port A into a file register, and now that file register has 8 bits. So let's look at hex 78. So what's the significance of this bit? Is it a random 1 or a 0? Is it always a 0? Is it always a 1? Is it related to something else in the universe? What's the meaning of the value of this bit after I copy port A into hex 78? Say again? That sounded promising, but I didn't catch the audio. Can you say it again? Alright, I got the volume cranked up now. Try it again. It will be 78 in binary. Well, this is a single bit, so it can't have the value 78. It's going to be a 0 or a 1. It's guaranteed. It's either a 0 or a 1. But what's going to control whether that bit is a 0 or a 1 right now?
Port 2, right?
Bit 2 of port A, or pin RA2. So yeah, we can think of that as port 2. But bit 2 of port A is going to get copied into bit 2 of file register 78. So let's suppose that the instruction we did for question 19 was a move FF. That's the simplest to write. Move FF port A, comma 0x78. So each of these 8 bits of port A is going to get copied to each of these 8 bits of of file register 78. Okay, so this bit 2 of file register 78 will be a copy of whatever the bit value was in bit 2 of port A. What is that bit in port A? Well, we set up tri-state A to say that this should be an input pin. RA2 should be input. And so if pin 2 of the chip was at 0 volts when we said move FF, then this bit will be a 0. And if pin RA2 of the PIC chip was at 2.5 volts or higher, then this bit of file register 78 will be a 1. It tells you what the voltage level is on pin RA2 of the PIC chip. And this is a physical thing, and it's unfortunate that we're doing this, synthetically, that we don't have access to a laboratory. But if we did, right, whatever the voltage was on pin 6, that's what's going to be in that third bit position of that file register. If pin 6 is disconnected, we're still going to have a 0 or a 1, but who knows what it's going to be. If someone happens to be leaning their elbow on the chip and they're touching pin 6 with their elbow, it's probably going to be 0 volts. If it's been sitting around for a while, it might have built up a charge and it might be high enough that it reads as a logic 1. If they've got a switch hooked up to it, right, which can deliver a nice clean 0 volts or 5 volts, we'll see a 0 or a 1. And the same can be said of this bit, because we've also said in tri-state A that bit 3 is an input, which means this bit of port A comes from that pin labeled RA3, which is pin 7. So this bit will be a 1 or a 0 depending on whether pin 7 of our chip is above or below, say, 2.5 volts. Let's see, someone says my volume sounds lower than usual. Can you raise it a bit? That's easier said than done. Because it's actually been fuzzing out. Let me try making a change here. Hold on one sec. Alright, how's that volume? Hopefully that's working better. If not, let me know. Alright, so these two bits tell you the voltage levels on pins 6 and 7 of the chip. Right? They come from this physical property of the PIC processor. This bit over here is a different matter. If we had set this bit of TRISA to be a 1, saying we're going to input from pin RA7, then this would also tell you the voltage on pin RA7. But since we've set this pin up to be an output pin, the value that we read from here is meaningless. Right? It's more or less effectively random. And the values of these bits are pretty much completely random to us because we have not specified anything about those pins on the chip. Maybe we've set them up to be inputs and they'll tell us if the voltage levels are high or low, but in this question, right, we're trying to do input from pins RA2 and RA3, so we're presumably controlling the voltage level on those pins to be something particular. But the other bits of file register 78, they're more or less random. They're not meaningful, other than bits 2 and 3. So they're not missing, they're always a 1 or a 0, but if you didn't specify those bits to be inputs, then you can't say anything about the value that you're reading from there. And in particular, you cannot assume that these bits are going to be zeros. Which is why when you're doing lab 2 and you're trying to look at, say, a particular set of bits, you have to use a bit mask to zero out bits that you're not interested in. So is this making sense? This is one of the more confusing parts of dealing with the PIC, is the whole input-output system, and particularly the tri-state registers.
I mean, it's, for me personally, it's not completely clear, but I mean, once I start using it a bit more often, I'll probably be able to understand the concept of it in detail.
Okay.
Could you be able to go over it like once more between like which pins are in each of the registers, or such as like where they come from, or where the inputs or outputs come from?
Okay. Let's do this. Let's do this in MP Lab, and then let's take a look at the data sheet. And this will give us like 3 different ways of tackling this. So let me run some quick MP Lab code here. So I'm going to do ADCON 1. That's always going to get set up for digital input. And let's just do this. Let's see, so if we had set RA7 to be the sum of RA2 and RA3, then RA7 would be meaningful. Well, RA7 would be meaningful, but remember, if we're reading from that bit, and that bit is set to be an output, we can't read that value. And I don't know if this is going to be reflected by the simulation, but let me try something with the simulation here. Let's build this and let's run it. I should have tested this first because it's probably going to bite me. Alright, there's port A. So I've got a 7F in W, I'm putting that into ADCON 1. I'm putting a 55 into W, and I'm moving that to port A. And guess what? Port A still shows a value of 0. Let me throw something else over here. Just so we don't have to worry about dropping off the edge of the code. So let me go ahead and run this again. Okay, I'm going to single step. I'm going to watch my variables, including port A. So I put a 7F into W. I put that into ADCON 1. I put a 55 into W, and now I move W into port A. And port A is still 0. Right? I said move a 55 hex right from W into port A, but port A did not change to 55 hex. Right? Why? Because port A is an input port right now. Because all 8 bits of TRISA are set to 1. Right? TRISA is a DF while most of the bits are set to 1. Okay, I don't know if this will work, but let's try it. We'll push my luck here.
It's the move VDF.
Thank you. Alright, 7F into ADCON 1. Now I'm putting a 0 into TRISA. So let's look at TRISA. Okay, so TRISA is a 0. I put a 55 into W and I move that to port A. Well, now port A is showing me 55. So not having this makes my move to port A fail. Alright, so what's going on here? Here's port A. Here's TRISA. By default, all of these bits are 1. That's the power on state. Okay, that's how the processor begins. And anytime there's a 1 in a bit of TRISA, it's saying the corresponding bit of port A is an input port. If it's an input port, I can't write to it. I mean, I can write to it, but it doesn't actually write. So when I try to write a bunch of 1s to port A, it didn't change the value of port A. But now if I go in here and I change all of these bits in TRISA to be 0s, then whatever bits I try to write into here is going to get written into that bit of port A because that's an output pin. Whatever bit I write into here will get written into that bit of port A because that's an output, and so on. And so by putting a 0 into
for those ports, we'd have to set a value to them, and then they would get transferred into port A by given some kind of command when clicked.
So suppose I wanted to set port A to look like this. We should be doing port B because port A's got some funny bits. But suppose I wanted to send these values to port A. Okay, 2 1s, 4 0s, and 2 1s. Okay, all I got to do is something like this. Move LW. See if I can remember how to do binary. Okay, so I'll move that pit pattern into W and then move that into port A. And so let's look at port A after I do this. And there's port A, C3 hex. Right? But again, if I don't do this setting up of TRISA, and I run this, right? Exactly the same code, but after I try to move that bit pattern into port A is still all zeros. The reason it didn't change value is because I told it that these bits were inputs, right? Remember, they default to ones. So I don't have write access to any of these bits. Now suppose I set TRISA to this. Suppose I just set these low 4 bits to 1 and the upper 4 bits to 0, and then I write this bit pattern to port A. What's going to be my final value in port A? Yes, so someone asked, is giving TRISA value enabling port A to be either input or output? Yes, that's exactly what it's doing. TRISA is enabling each bit of port A to be input or output. So let's give TRISA an interesting value. Alright, so I'll put this pattern into TRISA, and then I'll write this value out to port A. So now we've written TRISA, and now we load this bit pattern into WC3 and we write it to port A, and what does port A end up being? It ends up being C0. And that's exactly what we asked it to do. Because when we set up this value of TRISA, what we said is these 4 bits are output bits, and these 4 bits are input bits. Input, 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 output, 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 output. So even though I wrote some 1s over here and some 1s over here to port A, these are the only ones that actually got written. Because I can't write to these bits because they're inputs. So when I wrote to port A, the final value of port A looked like this. Alright, so that's your C0 hex. And we could do similar experiments on the input side. So my stimulus, let's just set up a couple of toggles. And we'll just throw an infinite loop here at the end. Alright, so I'm sitting here and I'm looping. And port A is a C0. If I fire my stimulus to set RA0 high, and I step my system, that low bit, right, corresponding to RA0, that just changed to a 1. And if I fire my stimulus to set that low, then that low bit changes to a 0. But if I change TRISA, so I'm going to change TRISA to look like this. Right, what is this 0 saying? It's saying RA0, yes, which is the first bit of port A, saying RA0 is an output pin. So let's compile that and run it. So we load ADCON, we load TRISA. So there's TRISA. And now we're going to load this value. I hit the wrong button. Let's do this again. Alright, so we load TRISA, we take this value into W, and now we're going to move that into port A. And port A is C1. Right? Why is it C1? Because we tried to write C3, right? 2 ones here, 2 ones here. We tried to write those, but this bit is an output bit, so the 1 got written. This is an output bit, so the 1 got written. These are output bits, so the 0's got written. This is an output bit, so this 1 got written. But these are inputs, so those didn't get written, so the value that we wrote was C1 hex. And now we're in an infinite loop. But watch what happens if I come to my stimulus and I try to set RA0 low. It doesn't change it. Port A is still a C1. And if I try to set RA0 high, that has no effect. And if I try to set it low, that has no effect. The reason that stimulus has no effect is because bit 0 of TRISA is a 0. We're saying RA0 is an output. And so we can write to port A and see that value, but we can't read from port A. And firing those stimuli are basically connecting that virtual pin of the PIC processor, pin 6, to either 5 volts or ground. But it has no effect on port A because that bit is an output port bit. So TRISA just basically says, is each bit input or output? And we've got 8 bits in port A, so we have 8 of these direction bits to specify. Alright, you've all done 270. I mean, you've all done 250. So, yeah, I haven't done 270 yet. So, let me show you the final word on I/O ports. It's this picture right here. Okay, this tells you everything you need to know about TRISA and about port A and TRIS-B and port B. Okay, this is a bit of the tri-state register. You've got one of these setups for each of your 8 bits in, say, port A. Okay, so port A is 8 bits wide. You've got one of these for each of your bits. If TRIS-A, if a particular bit is equal to a 1, you have a 1 coming out of Q, right? And that 1 gets inverted by this bubble, makes it a 0. It disables this buffer, so the contents of Q does not get sent to the I/O pin. It blocks the output operation. On the other hand, the value coming in from this pin goes through a buffer, goes into the D input of a flip-flop, and when you say read from the port, right, putting a 1 on this pin gets inverted to a 0, it drops the enable input on this flip-flop, which latches the data value inside here, sends it out of Q. The 1 that you're specifying to say read the port enables this buffer, so the value of that bit that just got read from the pin comes out of this buffer and it goes to the data bus. So this will tell you, you know, in an engineering 250 form, exactly what tri-state A and port A and tri-state B and port B are all about, right? And this is how most of the port A pins work. There's different details on here, so pins RA0 through 3 actually look like this. They have some extra detail in them. Pin 4 looks like this. Pin 6 and 7, and pin 5 is just really strange. Pin 5 is mostly used for this MCLR bar. MCLR is the major clearer pin, which you use to reset the system. and it's got a bar on top, so it's active low. So if you pull pin 5 low, it resets the PIC processor. If you disable that, then you can use it as just RA5, bit 5 of port A, but that's hard to do. Port B is a little easier to deal with. All the ports basically look like this, or like this. So don't be afraid to go back to your data sheet and dust off your 250 notes and dig into some of these pictures. There's nothing in here other than maybe tri-state buffers, which is just, you know, if you have a 0 going in the side here, this buffer is enabled, the input goes to the output. If you put a 1 in the side here, this buffer is disabled and the output is basically disconnected from the internals of this buffer. So it's called a floating output. It's also called being in the third state. This is a tri-state buffer. That's what the TRIS is in TRIS A, TRIS B. But you don't need to understand that level of detail necessarily to work with these things. All you need to know is when you want to do output, set the corresponding bit in TRIS A to a 0. When you want to do input, set the corresponding bit to a 1. And just do that once. You don't have to reset it to a 0 every time you want to output a value, because nothing changes this unless you change it explicitly. So in the beginning of your code, you set up ADCON 1. If you're using port A, you set up TRIS A. If you're using port B, you set up TRIS B. And then you're just good to go. Just read and write from port A or port B, depending on what it is you want to do.
Can you remind me what the ADCON 1 register does?
ADCON 1 controls whether we're doing analog or digital I/O. And if we comment this out and we run the same code, so I've set up, let me go back to where it was before. Let me make this a 1. Alright, so we've set TRIS A to be 4 1s, and we've written to port A, and you know, as we saw before, it doesn't write those lower bits because those bits are set up as inputs. So let's go to our stimulus and let's fire this pin to set RA0 high. And we still don't see that bit coming in on port A, even though we said set that pin high. It's ignoring it. Okay, why is it ignoring it? Because by default, all of these port A, a lot of these port A pins are set up to do analog input. Okay, so RA0 is also AN0, analog input 0, and the default is to do analog, which means we could load a voltage into there and we could translate it and figure out if that voltage was, you know, some value between 0 and 5 volts. But we can't read the values on port A unless we tell the PIC chip that we're going to do digital I/O. So that 7F that we put into ADCON 1, that's saying we're going to do digital I/O. And for Lab 6, we'll talk about analog I/O. We'll actually break down these individual bits and see why we have to set them to 1. But for now, just very beginning of your program, always put a 7F into ADCON 1. You can just take it as something that we have to do.
Thank you.
All right, so general question I get from people, is there a way to move part of a port into a register? And the answer is basically no. Most of our operations move an entire 8-bit register from one spot to another. So if we only care about 2 bits like RA2 and RA3 of port A, we still have to take all 8 bits from port A and transfer them into a file register. And some of those bits may be interesting to us, some of them may not. So typically what we do is we mask off the bits that we don't care about. So let's see an example. Suppose we want to write a bit of code to know if bits RA3 and RA2 are equal to 1 and 0. In other words, is port A bits 3:2 equal to 1, 0? Okay, so somewhere we want to set up TRISA to say we want to input from our registers. Well, TRISA defaults to input for all the bits, so we're not going to worry about that. We need to set addcon1 to 7F if we haven't already done that, but I'm going to assume we've already done that in the beginning of our program. Let's just look at this business of these bits. So here's what I can do. Let's move port A into the W register. So my W register looks like this. It's 8 bits. There's 4 bits I don't really care about, bits 7 through 4. There's a bit RA3 I care about. There's a bit RA2 I care about. There's 2 more bits I'm not interested in. And we want to know, is this something with this bit pattern? Is this bit a 1 and this bit a 0? Well, it's really hard to know right now because I don't know what these other bits are. This could be this, or it could be this, or it could be that, right? Since I'm not using these, since they're not meaningful to me, I can't just say, is my W register equal to this? Because I don't know that these bits are going to be 0 and those bits are going to be 0. W register could be equal to this, it could be equal to that, it could be equal to this. But in all 3 cases, the answer to my question is yes, those 2 bits are a 1 and a 0. So how am I going to detect that? Since I've got gibberish up here and gibberish down here, we mask off the gibberish. So we use a bit mask. So we'll AND the W register with the following literal. Four zeros, 2 ones, and 2 zeros. And after we do that, now WReg looks like this. Those bits are zeros because we ANDed whatever the values in WReg were with zeros. Those bits are still RA3, RA2 because we ANDed them with ones. And these 2 bits are zeros because whatever the bits were in WReg, we ANDed them with zeros.
Excuse me, Professor. Could you go over how you set RA3 and RA2 again one more time?
What do you mean how I set them?
So like you said RA3 and RA2 is a 1 and a 0. How would we like set those values in a binary number, say at the very beginning?
So I
feel like somewhere from the beginning, where it says like 3 to 2 equals 10, is that somehow related in a way?
So the setup here is I'm supposing that I've got my physical chip, okay, and I have a switch connected to pin 6 and another switch connected to pin 7. Okay, so this switch is feeding bit RA2, right, bit 2 of port A, and this switch is feeding bit 3 of port A, RA3. And this code that I'm developing is basically asking, is this pin on pin 6, is this connected to ground, and is this connected to 5 volts? Right, I want to detect the condition where this RA2 switch is low and the RA3 switch is high. So I'm just writing a piece of totally junk code to say, are these two bits of port A equal to 1 and 0 respectively?
Oh, okay, all right.
Okay, those bits are being set up in the hardware from outside the system, and I want to detect when that first one's high and the second one's low. So set up your tri-state register to read from those bits, set up ADCON1 to be 7F as usual, move port A into the W register, and then mask it to throw away the bits that we're not interested in. So after this masking operation, my W register is guaranteed to be all zeros except for these two bits, which will be the value of RA3 and RA2. So now if I say something like subtract literal from W, and I subtract that pattern, if it turned out that W-reg was equal to this, and I subtract this bit pattern, I'm going to end up with 0. And so I can say branch if the result was 0 to whatever section of code I want to jump to when I discover that my input was 1, 0. But if my W-reg was something like this, in other words, if RA3 was 1 and RA2 was 1, and I subtract this pattern, I'm going to end up with this, which is not 0. All right, this takes some thinking about, but this is the basic way we can analyze pieces of an 8-bit field. And it's basically two steps. One, use a bit mask to get rid of the bits that you don't care about, and then do usually some kind of logic or arithmetic operation to see if the bits that we do care about correspond to the value that we're interested in. So yeah, reminder of an AND gate. Right, that's your AND truth table. So if I set my bit mask to 0, the AND is always a 0. If I set my bit mask to a 1, the AND is always the same as the bit that I ANDed with. All right, let's see. Let's go ahead and take a 5-minute break, and I will post a reference to a resource you might find useful for thinking about bit masks. Let's take a 5-minute break, and then I want to talk about the access bit and reveal all the mysteries about that. So stretch your legs. I'll be back in about 5 minutes.